Thank you for the warm introduction. Today, like was mentioned, I'll be talking about interoperability in FHE with LayerZero Labs and Zama. Before we get started, I just wanted to give my background. My name is Matt. I am the developer ecosystem lead or head of DevRel for LayerZero Labs. My background is mainly on interoperability. I've been working at LayerZero for 2.5 years now, so I have a fairly decent idea about how cross-chain value transfer and cross-chain message passing works. But obviously, our friends here at Zama are the experts when it comes to FHE or fully homomorphic encryption. The topic of this conversation will really be to conceptually go through how we can think about using Zama with interoperability. What are the benefits that it provides? How does LayerZero work? And the ways that we can combine these two services to ultimately improve the way that we interact with DeFi on multiple chains. So with that out of the way, let's take a little bit of a step back and think about what are the trade-offs when it comes to being an app developer in today's blockchain world. Developers and users are forced to make trade-offs all of the time when they interact with various different smart contracts, when they build smart contracts, when they think about how their applications are put together. You are forced to decide between a security trade-off, a speed of execution trade-off, cost, and also the developer experience of working with the various platforms and services that you end up using. The same trade-offs apply to the blockchains themselves. Every blockchain has a unique value proposition that it is trying to sell you, the developer, and ultimately sell the holders of capital who need to move value between these chains. Similar opportunities around security, speed, cost, developer experience, and again, ecosystem opportunities if you are an asset issuer. So when we look at what is this cross-chain world that we live in today, we can think about it from the Electric Capital Developer Report in 2024. Year over year, the number of chains that users interacted with and that developers deployed to more than doubled. We saw an increase of 8% in the number of developers deploying to 5 or more chains from 2023 to 2024. So cross-chain interaction is way up, and it's mainly because we've had a Cambrian explosion, if you will, of new chains that are live, L1s, L2s, non-EVMs, the list goes on. What LayerZero stands to provide is a global ledger where you as the application developer, a DeFi developer, an asset issuer, are able to safely deploy to all of these networks using a permissionless, censorship-resistant, and immutable protocol. LayerZero at its core is all about making the capacity of moving data and value between chains as seamless as possible. And hopefully, as we'll talk about in a couple moments here, with Zama, we're able to make it protected by fully homomorphic encryption and make that value transfer not just encrypted, but private. We'll get into some of the reasons of why that's valuable next. So historically, when we talk about value transfer and just any type of cross-chain system, the background has often been very, very difficult for users and developers alike. Message passing bridges with fixed validator sets, like the one that you see here, have very, very high centralization risks associated with them. The reason is that when you connect two different blockchains, every application that is using this connection is reliant on these validators telling the truth. If you use a multi-chain bridge, something like a middle chain, if you use a centralized validator set where you don't have a say in which validators are verifying that these messages are legitimate, you run the risk of being fully dependent on them for all of the events that are coming cross-chain. And this is a very difficult problem to solve because it leads to misalignment of incentives. You now have to worry about these validators colluding in ways that could threaten not just your application, but every application that uses these services underpinning the bridge itself. With that in mind, when we look historically at some of the largest hacks in the space, 3 out of the 5 largest hacks that we've seen in the blockchain industry have come from these monolithic bridge security providers that have had an exploit in their core contracts, either due to upgradability or direct issues with their validators going rogue, which has led to billions of dollars in losses because developers and applications cannot trust their bridge infrastructure. Ultimately, this problem is directly related to the fact that every application, every single asset is forced to use the same validator set. there is no way to diversify your validators as an application developer. And this problem relates also to privacy as well. When you're building a cross-chain application, the way that these apps work is that you are producing a function event signature on a source blockchain when you write that you want to move assets from one chain to another. The problem is that those validators are directly listening for those event signatures, and all of that data is public on a public blockchain. Any validator can read your intentions on one chain and front run the opportunity that you're trying to arbitrage on the next chain. The issue here has to do mainly with the fact that for any type of complex DeFi application that you're building that relies on more than one chain, the ability for validators to directly see your intentions of what's going to happen next or what you're going to compose with impacts your ability to achieve capital efficiency and ultimately makes it difficult for you as a developer to really implement the type of systems that you're trying to build on top of. The second concern here is that because validators know the type of transactions that you're submitting on a source chain, they are the ones that ultimately decide when they are delivered. The fact that you have permissioned delivery or permissioned relay in a lot of cases means that once these validators see some transactions coming in, they may be biased to which transactions get executed first because they have skin in the game. They have financial opportunity for taking advantage of this ordering. So for us, privacy is a major concern that needs to be solved in interop as well, because it leads to this centralization of actors and ultimately centralization of data, which the most coordinated systems or most coordinated validators can take advantage of. The other thing to keep in mind as an app developer is that if you use a monolithic bridge system or a fixed validator set, you are forced to pick between one of these 2 points. You have to pick and make a decision cost trade-off with your application on whether you are going to have relatively low fees for your cross-chain implementation, but relatively low security. Obviously, it's not directly linear in the real world, but as a simplification. Or if you're building a DeFi application that needs maximum security, every single transaction that you send cross-chain is likely to have very high cost associated with it as well. The other pain point that we have here is that switching between point A and point B on this cost curve is very, very high. Once you implement your smart contracts, unless you implement them intentionally, you can run into a lot of risks where changing validator sets is quite difficult to do in a scalable way and in a way that is not introducing new vulnerabilities into your smart contract code. So there is a danger here as well for anyone who's working with cross-chain systems. Ideally, what we want is a way to have a modular security stack, a way for us when we build cross-chain systems to pick any point along this curve that fits the use case and the opportunity cost for our application. Some applications trade off centralization, right, as we mentioned before, for the ability to have higher capital efficiency in market for things like intents, for example. And so there are a lot of opportunities where we can't just have a fixed point on this curve. We need to be a lot more tailored to what applications are building. Ideally, the solution that we build with should allow us to have any one of these points along the cost curve as our ultimate, application setup, okay? So with that in mind, what is LayerZero? LayerZero is an immutable interoperability protocol for building universal applications. What does that mean? With LayerZero, we allow any developer to create a smart contract that can move any arbitrary call data from one chain to another using the LayerZero endpoint. The LayerZero endpoint is a stateless smart contract that's deployed currently now on 150 plus mainnet networks that allows you, the app developer, to select the type of security that you will use for your application. It lets you decide the execution requirements, namely the gas limits and the message value that will be delivered. And it lets you specify for your security the not only type of security that you use, but also the number of security providers that are available within your stack. This ability for LayerZero to have maximum configurability makes it so that you can build any type of cross-chain system with any type of opportunity cost that you need to tailor for, and ultimately know that your contracts are still secure, they're using the same interface design and logic, and that there is a battle-tested system in place that has worked for hundreds of other applications and asset issuers. At a high level, the way that LayerZero works is pretty straightforward. All you need to do is interact with your smart contract that is inherited or implemented a send function. This send function calls the LayerZero endpoint. It provides a message that you want to send in the form of raw bytes, a destination chain that you're going to be sending to, and a configuration about this pathway from a source chain to destination. Within this path, you can see that after a transaction is submitted on a source chain, your selected, what we call DVNs or decentralized verifier networks, listen for proof that this message has been submitted on a source chain. These DVNs then go and relay that verification of the message to a destination chain. On the destination chain, you'll have another smart contract that you've deployed that has a configuration registered here about time to finality, about the expected DVN addresses that you're using, and about the threshold for security that's needed to mark this message as verified. Once this message is marked as verified, finally an executor can go and deliver this message end-to-end to the final smart contract and ultimately apply the state change that matters to the user using this contract. So with this system, the ability to send a message on a source blockchain, automatically have service providers verify that this message is legitimate, and then execute on that verification enables you to build LayerZero messages that move any arbitrary call data, function selectors, things that you need to essentially orchestrate on the destination chain, or asset transfers, or finally data and asset transfers at the same time. LayerZero is a very flexible system in that you can move basically any arbitrary state that you need between multiple blockchains. Looking a little bit deeper at the LayerZero endpoint, the way that endpoints work is simply point-to-point. Anytime that you want to send a message from one chain to another, you simply have to look for the LayerZero endpoint that is deployed on that chain. You will, again, within your application, set up a configuration or what we call an omni-chain application config, and then be able to send messages directly from point to point within this setup. The way this works under the hood is that we have a verification layer that we call the message library. The message library is fairly straightforward. The way that it works is that it's another smart contract that LayerZero deploys underneath each endpoint. Every endpoint can have an appendable list of libraries to choose from, and these libraries let the endpoint do different things on chain. For example, the most common libraries that we work with are for sending and receiving arbitrary data. But there are other library types that you can take advantage of too, like read libraries. These read libraries let you read arbitrary state data from other blockchains and bring them back to a source chain in a single contract call. So the advantage here is that with LayerZero, as new utilities or new types of implementations come out that are desirable, we can easily add these appendable libraries to our stack and make LayerZero not only more flexible, even though it's an immutable smart contract, but allow you to opt into new future proofing as it comes online or is desired. When we talk about DVNs, what are decentralized verifier networks? Again, these are the validators that are underneath, allowing you to actually verify that a message or state transition that happened on a source blockchain really happened in that source chain state. The problem with blockchains right now is that with the normal nodes that you have underneath a chain, you have to essentially trust that from another chain, state transitions have happened because the nodes on Ethereum are not sharing the same state as the nodes on Solana, for example. So these DVNs are ways to basically prove that state has moved from chain A to chain B. The types of DVNs that you can use are ZK-like clients like Polyhedra, which creates a proof attestation that the message has been submitted on the source blockchain. You can use established Web2 entities like Google Cloud if you just want a centralized solution to relay messages for you. You can use a middle chain bridge like Axelar if you want to have a full blockchain's consensus reach for every message that you're sending. Or you can run your own validator. You can create any verification schema today that uses a simple contract interface to relay state from chain A to chain B. And what this eventually gives you is that whenever new validation comes online, think about with ZK proofs over the last 5 years and how much development has happened, you are able to easily take existing applications built on LayerZero and update their configuration so that they're using the latest and greatest security that's available to them for cross-chain messaging. As part of this configuration, it means that you as an app developer have a lot of flexibility and future-proofing available where if new validation comes online, you're not forced to upgrade your entire smart contract, but rather update essentially a pointer in your smart contract code to a new address. In terms of execution, LayerZero also abstracts away a lot of the smart contract calls that you can make on chain. On the left-hand side here, you can see what is a typical, what we call atomic smart contract call. The LayerZero executor will call an endpoint once the message has been marked as valid. It will call a destination application, and then your app can make as many other calls within that same stack trace as it wants. The challenge here, though, is that sometimes we want to do operations on the destination chain that aren't bundled all in one. The problem here is that if a single call fails, let's say on smart contract C, this entire stack on the left-hand side reverts. What we've introduced is a concept known as horizontal composability. With LayerZero, when you send bytes cross-chain that you want to do something with, the executor will call the LayerZero endpoint, which calls your application. Your application does its business logic change. For example, this could be minting tokens, calling Uniswap, interacting with Aave. And then, if you have a second operation that needs to happen afterwards, you can store arbitrary bytes for later execution back into the endpoint. And then the executor will do a second entirely separate call on your behalf. This is very, very helpful for DeFi applications and DeFi operations, for example, because when you do cross-chain state transfers, oftentimes you need to ensure that the tokens have been transferred before you do an operation like staking or swapping or executing an exchange of value. This ability to split contract calls into two different atomic steps means that if something goes wrong with staking or swapping or something else in this call stack, I can still guarantee that my tokens have arrived safely on the destination chain, and my users don't have anything to worry about from their end in terms of the bridging operation that took place. LayerZero also allows for gas drops from a source transaction, meaning that as an end user, if I need to fund a wallet with a destination gas token like Matic or AVAX or BNB, I'm able to do it directly from the source chain only using my source chain gas, which is very, very helpful when you're trying to onboard users to a new ecosystem or when you're trying to pre-fund wallets for certain DeFi operations that you know they'll be taking on the destination chain. Zooming out a little bit, one of the main primitives that LayerZero supports is omni-chain transfers via our OFT standard. The way that OFTs work is relatively straightforward. It is a smart contract that sits on top of any other existing fungible token standard. So think about ERC20 for any EVM chain. Think about SPL tokens for any Solana VM. Think about Coin for Sui. The list goes on. There are multiple different token standards. OFT is a way to say, I want to define common rails on how value moves across not just every EVM chain, but every non-EVM chain as well. This ability to debit tokens on a source chain, meaning removing them from circulation, send a LayerZero message that these tokens have been removed from circulation, and then receive that message and credit the same amount to a destination wallet, means that we can seamlessly set up asset issuers for success. They can deploy their smart contract on multiple different chains. For example, you could look at USDT, Tether, and be able to seamlessly debit Tether on one chain and credit it to the correct user on destination. Where I think this gets interesting for Zama is talking about how we include encryption into this cross-chain ecosystem. Zama, as you guys may be aware already, allows for you to have within the EVM a Solidity contract library that allows you to not only point to encrypted state, but hide it from the other participants on the chain as well. You, as the actual client user, are able to prove that anything that you needed to happen on chain has happened, but you're not sharing that those state transitions have happened with anyone else. This is very interesting, and I think will play a much bigger role within LayerZero in years to come, because as we mentioned in the beginning of this presentation, right, interoperability ultimately suffers from this common issue of you publishing public state about what you want to do on chain with every other actor on that ecosystem. With something like encrypted ERC20 tokens, you could have two encrypted ERC20s, one, for example, on ETH mainnet, one, for example, on Linea. And when I want to transfer tokens between chains, I can simply use the pointers that Zama provides to point to state transitions where a user proves that they have sent tokens on a source chain. It sends a LayerZero message to call the pointer to credit tokens on a destination chain. From the user's perspective, we don't know which wallet actually owns these assets or the amount, but the client can easily access on each network the fact that tokens have been debited on a source chain and tokens have been credited on a destination. As Zama rolls out more and more support for chains beyond ETH mainnet, this will become more and more valuable. But I also want to provide you guys with some things that are actionable that you can take away with today. How do I read omni-chain data and state? How do I take state from other blockchains that Zama may not be on yet and bring them to ETH mainnet so that I can do things that are interesting with fully homomorphic encryption? Well, looking back at our flow, LayerZero takes advantage of this via what we call our library mechanism. In the original flow, I remember I walked through how we send, we call the endpoint, these validators pick up that this message has been sent, we verify on the destination chain, execute. Great. If we wanted to do this previously, we would have to do some very complex coordination of contract calls, which I don't think anybody wants to sit through. So what LayerZero implemented was called LayerZero Read. LayerZero Read is effectively a way for you to not only interact with your source chain that you want to have some state change triggered on, but also pull data that might be relevant to that state change from multiple other networks using your DVNs. Essentially, the way that this flow works is that you will make a request from your source chain. Your DVNs will go and fetch relevant call data from chain A, B, C, whatever chains that you define, and then return all of that data appended as a bytes array back to your application for you to execute upon. The benefit here is that with LayerZero Read, you can listen to any arbitrary data that's happened on any other blockchain, bring it back to ETH mainnet, and using Zama today, you could prove using the pointers contract, even if it's not using a coprocessor on a non-mainnet chain, you could still prove that those events have happened via the pointers being brought back from LZ Read. I think this is something that's very interesting to look into from a perspective of understanding better how Zama can be expanded to new chains faster and faster. And I think that this is an opportunity to play around with the FHE library in Solidity and see how you can implement it on non-mainnet chains like BNB, Avalanche, Base, and then read state data about what pointers have changed, bring that back, and then execute upon. Outside of that, the way that LZ Read is different from normal LayerZero messaging is that with a normal LayerZero message, when you send some arbitrary bytes data, that's the bytes that you receive. So a bytes message gets sent, a bytes message gets received from the endpoint. With LayerZero Read, it's slightly different in that the bytes that you request are differ from the bytes that you respond with. So a request is sent out and emitted as a packet event, and then a response is delivered back to the source chain. So ultimately, this flow works essentially the same way. You'll create a query that you want to query on a destination chain. It will be emitted out to your DVNs and execute. Those DVNs will go and fetch from a target contract and at a target block number or timestamp with the relevant call data, what the state is, and then return back to your application. This state is a formatted bytes array for your application to use. Once that's returned, the verification gets attested, and then the executor goes and delivers that final call through to the application. This means that with LayerZero Read, you're able to not only fetch data from multiple different blockchains, you're able to actually compute on that data off-chain and format the exact bytes response that you want before it arrives directly to your application, which can be very, very valuable for anyone who's working with any type of data manipulation that you need or making multiple types of requests off-chain. One of the key use cases that we've talked about already with this in terms of DeFi is being able to, for example, fetch pool pricing from multiple different chains and bring them back to operate on for your application. If you needed to determine pool prices for, let's say, USDC and ETH from several different pools and find the best price, you could use LayerZero Read to fetch this pool data on Ethereum mainnet, on Polygon, on Avalanche, bring that data back, and then choose the best route for your users that way, all directly on chain. So with that, I know I've brought up a lot of technical topics. I just want to open up some questions and maybe see if anyone is interested in talking a little bit more about the interplay of interop and FHE. Thanks.